a lesser density between the two higher densities. That's all that's happening. And it's basically because of those various frequencies that are being absorbed from the sun. One of them is the Lyman alpha line. So if you do any astronomy, you want to get your H1 alpha, and you look at various nebulas in the sky at that frequency, at that specific frequency. I see, it's the Richardson's equation, 1 over lambda to the 4th. And that's why the sky is red and why the sky is blue. It's optical dispersion law by, I think it's Lord Rayleigh. Yeah, look at what? Oh, and meteor scatter. My friend really had fun with this, and this is about the E layer height, so about 50 to 80 miles. So if you're doing meteor scatter, you're right at the E layer. And like I said, my friend was in Albuquerque, New Mexico, just south of Albuquerque, and he worked someplace in western North Dakota. Another thing we used to do when I was in Albuquerque was to bounce off of balloons. So some of the folks in Colorado would shoot up balloons, and they would be just weather balloons, 12 to 20 feet in diameter, and we would bounce VHF signals off of them. I did a lot of single sideband weak signal work when I was down there. I didn't get into VHF FM until I was up here.
So is this the height that the meteor, the atmosphere is dense enough that the meteors really start to ionize and burn up?
Yes. This is where most of them burn up. Some of them actually do hit.
If they're big enough to start with.
Or they're slow enough.
Yeah. Oh, yeah.
Yeah. And up to 10 seconds, and they're good for 2 meters. So they're 70 centimeters doesn't work very well, 6 meters doesn't work very well with meteor scatter. But what I would like to advocate is people starting to try single sideband 2 meters, and you would be amazed at the range you get compared to FM. You'd be yes. I have a loop that I use a 70 centimeter loop and a 2 meter loop, and I have a 6 meter loop too. And it's great fun. It's an interesting mode, and maybe 200 to 300 miles. You might have to go up to 100 to 200 watts. Some of the people do get really insane, and they do go to a kilowatt, but you'd better be very, very careful because you've broken the FCC's little guidelines of danger. Don't get really close to those, or else you'll cook various body parts. It's dangerous. So most people only use about 50 watts, but you still don't want to aim it at people. You can put it on top of your car, but not on top of your cabinet. This one's really fun. But the problem is, well, see, I'm from the Midwest where auroras, the North Magnetic Pole is near Hudson Bay. So in Wisconsin, I was much, much closer to the North Magnetic Pole than I am here. I've only seen auroras once here. But you can still bounce your signal off of these. And this is good for 6 meters, 2 meters, and 70 centimeters. For 1296, it tends to cut right through. Lower than that, about 10 meters, it also doesn't interact properly. But those 3 bands in the amateur frequency chart, they seem to work pretty good. And you can get decent distance up to 700 miles. So you just have to find when the sun is active again, whenever that's going to happen. Oh, this is something that's interesting. We might run into a D-star with the 23 centimeters, 1296, well, rain scatter. And we get heavy enough rain, and what you need is a heavy enough rain, and the raindrops need to be about the same size over a wide area. And you can get rain scatter. So it will actually, you can bounce your 23 centimeter signal off, and we can get 120 miles. Which means, oh, well into Washington. Where would that? Seattle?
Well, Fort Lewis is 129 miles.
Yeah. Okay. And then the mountains, we get some added distance too, so we might want to look at that. I got this one. I had to look up and try to figure out the difference between troposcatter and tropoducting. troposcatter is you're bouncing off a change in the refractive index, but it's a broad range in the refractive index as it changes slowly. So you're basically like you're bouncing off the ionosphere, only it's the refractive index of water in the atmosphere. So what's really interesting is if you get a temperature inversion, all of a sudden you get a sharp edge of the what did I just say? Refractive index changes quite rapidly. That's where you can get tropoducting. So you can get a nice layer where your 2 meter or even, let's see, I think 6 meters will work for tropoducting too. It will get caught inside. Let's see, I got a picture. Yeah, it will get caught inside like this, and it will require a change in refractive index to actually pop out again. So you might not work anybody because it never pops out. The signal stays inside this duct all the way around and it never comes out. If it does, you'll be able to work somebody up to thousands of miles.
Let me give you a small example of how I actually observed this one time, watching my television set at Cape Disappointment. Actually, it was a North Head Light. It was a very stormy night, a very stormy night. And I would flip, I'd normally get a real fuzzy television signal, but I flipped to channel 2. And there's a beautiful picture from San Diego. No audio, the FM was gone, but the picture was perfect and lasted for about 10 minutes.
That's 1,500 miles?
Yeah, about 1,500 from Cape Disappointment to San Diego.
And the FM was probably...
The FM was gone.
Too low, okay.
Yeah.
No sound at all, right?
No sound.
Now, the difference between troposcatter and tropoducting is that you need that sharp layer to get ducting. If you don't get that sharp layer and you have, normally this happens in the summer, humid days, and you're going to have a nice change in the specific, I want to say specific gravity, wrong thing, refractive index. It's going to slowly change and you're basically just, this is like mirage in the desert when you see water and it's not really there, you're actually seeing a reflection of the sky. This is the same thing, only with radio waves. And you can get some decent distance, 250 miles, pretty good, but you're just bouncing, you're not really bouncing, you're just refracting, just a little bit. The ducting, it gets caught in that in-between layer and it stays there for many, many miles, like 1,500 miles. And channel 2 is right near 6 meters.
Yes. It's down at the bottom end of it.
No,
yeah.
it's 5 meters, right?
Oh, channel 2 is, I don't even know what the frequency is now.
I think that's why we lost 5 meters after World War II, it's because TV. Okay, tropoducting, let's see now, sporadic E's. This one is interesting because in the E layer, you can get clouds of ions. And sporadic E's have to do with the clouds of ions. Sometimes these clouds can be a few hundred miles wide by a few hundred miles long by centimeters thick. So it's just bouncing off this thin cloud that's going through the ionosphere, and that has to do with specific ion frequencies coming from the sun. So they can't really predict it when the sun's going to do certain things, but you're going to get these nice layers, and what happens is there's certain times of the day and there's certain times of the year. So times of the day is from 8 o'clock in the morning until, what does that say, 2400. Well, it's best in the middle of the day, so while it's sunny. Also, April through August, are the best. So the summer months during the high light times of the day, sporadic E's. And it also has to do with solar activity. So you want to see when specific frequencies are being shot off from the sun. And this is also mid-latitude, so we're right on the northern edge of this. The further south you go, the better it's going to be. But, Frank, if you point south into South America, you can use sporadic E's to get from here to there. But you need to keep your eye on the reflectors and go, the sporadic E's are happening. But, like I said, summer during the daylight. So you should be able to get some nice DX out of this. What sort of distances?